Previously, we've discussed the topic of partial derivatives. Let's suppose we have a function whose contour diagram is given as follows. I'm going to focus on the point 1, 2 in the xy plane, and here my change in x is given by about 0.2 as I read the grid values, and here in the y direction about 0.2 as well, and we can see how the contours are labeled. Now, we've talked about how to compute the partial derivative with respect to x at the point 1, 2. That would be the slope of the surface in the x direction at the point 1, 2. And we can see because the contour values are becoming larger, the partial with respect to x at this point has to be positive. We know that the partial derivative with respect to y at the point 1, 2 records the slope of the surface in the y direction, and we can again see, because of how the contours are labeled, that the partial with respect to y would be positive. We also know at a point how to estimate the partial with respect to x. We can use a change in z divided by a change in x. So for example, we could look at the change in z value when we go from the contour, this contour, unto the one where x is 1.2. Likewise, if we want to estimate the partial with respect to y at 1, 2, we would use this point right here, and we would go up or down a certain distance, delta y, and we could estimate the partial with respect to y. But now suppose we want to look at something different. Let's suppose we're starting at the point 1, 2, and we don't want to look at the slope in the x direction, not necessarily the slope in the y direction, but the slope in some other direction. Now the way we would specify that direction is that we would start with a unit vector. So in this case, I'm going to choose the unit vector 1/2 root 3 over 2. And what I want to do is I want to try to compute the slope of the surface in that direction. If I had a different unit vector, then I would get obviously a different slope. So we're going to focus for the next few minutes on just this unit vector. And what we're trying to do is we're trying to compute the slope of the surface at this point in the direction of that unit vector. We give that quantity a name, given a function and a point and a unit vector. We want to find the slope of the function at that point in the direction of u. And we call this quantity the directional derivative of f at the point x naught, y naught in the direction of u. And we use this notation. So the x naught, y naught keeps track of the point, f keeps track of the function, u keeps track of the unit derivative, and d is obviously for derivative. Now we can estimate this quantity using a formula or the contour diagram. What we do is we start at the point x naught, y naught in the direction, and we move in the direction of u to a nearby point, x1. This should be x1, y1. Then what we do is, instead of taking a change in z divided by a change in x, we take a change in z divided by a change in distance. So let's do a simple example. We're going to go back to the contour diagram you saw a moment ago. U is 1/2 root 3 over 2. X naught, y naught is 1, 2. So we're going to move just a little bit from 1, 2 up to this point right here. So x naught, y naught is 1, 2. And if I move up to this point, the x value at this point appears to be 1.2, and the y value appears to be, we'll say, 2.35. So we're not just moving in the x direction, we're not just moving in the y direction, we're moving in the direction of this unit vector. So this point is about 1.2, 2.35, and it falls on the contour where z is equal to 14.6. Then I have this point, x naught, y naught, which is 1, 2, and it falls on the contour where z is 10.95. So if I want to estimate the slope in this direction, one way to do it would be to take the change in z values between these 2 points and divide it by the change in distance, the distance between this point and that point, which I could get using the distance formula. So the change in z, that would be 14.6 minus 10.95. We read that off from the contour diagram. And we use the distance formula to find the distance from this point 1, 2 to 1.2, 2.35. So this is coming from the distance formula. It's more complicated than just a change in x or a change in y. And if we simplify this quantity, we get about 9.25. And that makes sense because if we look at the contours, if we're standing at this point and we look in the direction of that unit vector, we see the z values are going up. Now we want to be a little bit more systematic about this. We're going to keep the unit vector looking like this, and we're going to move a certain distance, h units, in the direction of the unit vector. And we're going to assume that h is small, and eventually what we're going to do is we're going to look at those slope approximations and let h get closer and closer to 0. In other words, this red dot is going to get closer and closer to x naught, y naught. So this length is h. That's the unit vector. For my picture, it looks like h is about 1/3 because this blue vector is about 1/3 the length of u. The vector u has components u1 and u2 in general. So here's our point x naught, y naught. To get to this point right here, we move h times u1 in the x direction, and we move h times u2 in the y direction. That's because these are the components of u, and this vector has length h. So the coordinates of this point, which I'll call x1, y0, 1, are given by x0, y0 plus h times u1, u2. Now let's go back and take a look at that change in z over change in distance. We know from the previous page that x1 equals x0 plus hu1, y1 equals y0 plus hu2. So if we substitute this in, y1 in here, and x1 in there, we're going to get some simplification. We'll have some cancellations, and everything will reduce to be just h. That's because the square root of u1 squared plus u2 squared is a unit vector. U is a unit vector. A simpler way to see it geometrically is just to realize that this u is a unit vector. So if I move h units in the direction of a unit vector, this length, that blue length, is actually just equal to h. So we know what the denominator of this expression is. Let's take a look at the numerator. Here's where we're going to use what's known as the tangent plane approximation. At the point x0, y0, this is a formula for the tangent plane. F of x0, y0 plus the partial of f with respect to x at x0, y0 times x minus x0 plus the partial with respect to y of f evaluated at x0, y0 times y minus y0. Now, if h is small, that means that this red dot will be pretty close to that red dot, probably closer than it is in this picture. What we can do is we can replace f of x1, y1 with the tangent plane approximation. So what I'm going to do is I'm going to take x1, y1, and I'm going to substitute it into the tangent plane formula. Now, there's going to be some cancellation. Here's f of x1, y1 minus f of x0, y0. This is what I get when I substitute x1, y1 into my tangent plane formula, minus f of x0, y0. Now you can see how this quantity and that quantity are going to cancel. And this is approximately equal to because we replace this quantity with its tangent plane approximation. So this quantity will cancel and this quantity will cancel. y1 minus y0. That's hu2. x1 minus x0 is hu1, so I can replace this with hu1 and this with hu2. So this simplifies to be h times the quantity, the partial of f with respect to x at x0, y0 times u1, plus the partial of f with respect to y at x0, y0 times u2. So that is the numerator, an approximation of the numerator, provided h is small. And here we have the denominator. Let's put all of this together. So the directional derivative, the slope of f in the direction of u at x0, y0, is approximately the change in z over the change in distance. The numerator from the previous page is this, and the denominator is that, just h. We want to know what happens as h gets closer and closer to 0. In other words, the separation distance between the 2 points that I'm using becomes smaller and smaller. So we're going to take the limit as h goes to 0. Now, we substituted this in. As h goes to 0, notice how we have an h here and an h here. Because h is not 0 when we take the limit, those cancel. And so we simply have the partial with respect to x at x naught y naught times u1 plus the partial of f with respect to y at x naught y naught times u2. So again, we're taking the limit as h goes to 0 and the h's cancel, which is what we're left with right here. Now this is a sum of two products. It is a dot product in disguise. The second vector in the dot product is our unit vector u. The first vector in the dot product is a vector made up of the partial of f with respect to x and the partial of f with respect to y, each evaluated at the point x naught, y naught. So the directional derivative in exact form is given by the dot product of two vectors. And we call the vector made up of the partial of f with respect to x and the partial of f with respect to y at x naught, y naught. We call it the gradient vector evaluated at this point, and we sometimes denote it with a little upside down triangle. This is sometimes known as the nabla symbol. So what this says is that if you know the partials of a function, the partial derivatives at a particular point, and you have a prescribed unit vector telling you what direction to look in, you can find the slope of the function in that direction. That means the partials of f with respect to x and y really tell the whole story. So let's take a look at a particular example. Suppose z equals f of xy equals x squared plus y squared plus xy plus 2x plus y. We're going to look at the unit vector 1/2 root 3 over 2, and x naught, y naught is 1, 2. And this is actually the precise function whose contour diagram we have here. So we see that an estimate of the slope is 14.6. Now let's do it exactly. We need to calculate the partial of f with respect to x, the partial of f with respect to y. We have f. We need to substitute our points in. We need to take our vector u, our unit vector, and compute the dot product. So here we go. The partial of f with respect to x is 2x plus y plus 2. And the partial with respect to y of f is 2y plus x plus 1. You can check that. So the gradient vector is a vector made up of 2x plus y plus 2, 2y plus x plus 1. If we substitute 1 in for x and 2 in for y, this will simplify to be 6, 6. So that's going to be a vector pointed to the right and up. So you may want to check that if I substitute 1 in for x and 2 in for y, I get 6, 6. So that means that the directional derivative of f at the point 1, 2 in the direction of this unit vector is the dot product of the vector 6, 6 with u. So here's vector 6, 6. Here's my unit vector u. If I compute that dot product, I get 6 times 1/2, which is 3, plus 6 times root 3 over 2, which is 3 root 3. That is approximately 8.2. And you know, that's not too far from the approximation we had a few pages ago, which was about 9.25. So again, to compute the directional derivative, you need the gradient, which means you need partial derivatives, you need a unit vector, and you need to compute the dot product. So here are some problems for you to do in preparation for class. So I'm giving you a function, asked you to compute the gradient of the function at 1, 2, and ask you to compute a directional derivative, and then here's a second function as well.